Hi, everybody. My name is Andy O'Bannon. I'm a lecturer in physics here at the University of Southampton, and I'm going to talk about a question you've probably never thought about before. Is our universe a hologram? And more specifically, I'm going to talk about my research, and if I had to summarize my research in a single sentence, it would be this. I use a tool from string theory called Holography to study strongly interacting systems. And so what I'm going to do is I'm going to go through each one of these things and try and explain what it is, very briefly, why you should care, and how they're related to each other. So, in the rest of the talk, I'm going to go through each one of these things one at a time. So let's start with string theory. To explain string theory, I need to start with the two major achievements of 20th century physics, namely quantum mechanics and Einstein's relativity. So let's start with quantum mechanics. Broadly speaking, quantum mechanics describes the very small, so roughly speaking, things at the size of atoms and smaller, subatomic scales. So to give you an idea of how big this is, let's take a normal everyday object like an iron skillet. Let's say that's about 30 centimeters across. Well, we know microscopically that iron is made of atoms, and there's an artist's depiction of an atom there on the right. How big is an atom? Well, it's about 10 to the minus 8 centimeters. And this is my chance to stop and remind you, if you don't already know, what this notation means, 10 to the minus 8. In this talk, we're going to see a lot of very small numbers and a lot of very big numbers, and I use this notation. It's called scientific notation, and it's a shorthand way of writing very big and very small numbers. So let's start with very big numbers. So we would write, for example, 10 to the 2, 10 to the power 2. That means 10 times 10, or 100. 10 to the 3 is 10 times 10 times 10, which is 1,000, and so on. All you have to remember is that the number up there, the 2, the 3, the 4, or whatever it is, tells you how many zeros come after the 1. And then for very small numbers, we put a minus sign. So 10 to the minus 2 is 1 over 100, or 0.01. 10 to the minus 3 is 1 over 1,000, and so on. And in this case, all you have to remember is that the minus 2, minus 3, or whatever, is the number of zeros that come before the 1, or to the left of the 1. So going back to the iron atom, it's about 10 to the minus 8 centimeters, which is very small. But as this picture shows, an atom is not a fundamental particle. It's made of smaller things. In particular, we know that at the center of an atom is a nucleus. And then surrounding the atom, orbiting around it, whizzing around it, are things called electrons, particles called electrons. Now, as far as we know, electrons are fundamental particles. So what that means is that at this moment in history, we have no experimental evidence that they are made of anything smaller. However, we know that the nucleus is not a fundamental particle. It is made of something smaller. So let's take a look at that. So again, first of all, how big is a nucleus? Well, it's about 10 to the minus 12 centimeters. So that's about 1/10,000th the size of the atom, which was already really small. And again, this is an artist's depiction of a nucleus. And as this depiction shows, we know that a nucleus is actually not fundamental. It's made of smaller things, namely two kinds of particles called protons and neutrons. How big is a proton or neutron? Well, it's about 10 to the minus 13 centimeters, so about 1/10 the size of the nucleus. And it doesn't stop there. We know that the protons and neutrons are also not fundamental particles. They're made of even smaller particles called quarks. And how big are the quarks? Well, this is where we get to the boundaries of the experiments. So I can't actually say how big a quark is, but I know it's smaller than a proton or neutron. So I know it's smaller than 10 to the minus 13 centimeters. And at the moment, that's where the experiment stops. So right now, as far as we know, the electrons and the quarks are the fundamental particles. And the theory, or the equations that describe the motion of these particles and how they interact with each other, is called the Standard Model of Particle Physics. It was developed basically after World War II, the generation after World War II, back in the 50s and 70s. I've shown some of the people involved, by no means all of them. The ones I show here are a lot of the Nobel Prize winners, people who won Nobel Prizes for their work on the Standard Model of Particle Physics. And the key point, the Standard Model of Particle Physics was based on quantum mechanics, which was really developed before World War II, the generation before, in the 20s and 30s. And here again, I've shown some of the people involved. Again, some Nobel Prize winners, not even all of them, but some of them. You may recognize some of the names, like Schrodinger, maybe Planck. And actually nowadays, probably the most familiar is Heisenberg because of the show Breaking Bad, which I admit I've never seen. However, I also have a personal connection to Heisenberg because my very first job, the very first time I ever got paid to do physics, was at the Werner Heisenberg Institute in Munich, Germany. And it was very intimidating, my first day on the job, because when I got there, on the very first day, I didn't have an office. It wasn't ready. My office wasn't ready for me. So they put me in Heisenberg's original office, which still had his original desk in it. And so I was sitting at his desk. And then the room today is, the walls are covered with pictures of Heisenberg. So it was very intimidating, my first day as a real physicist with, dozens of pictures of Heisenberg staring down at me, sitting at his desk, So no pressure. But anyway, one of the fundamental principles of quantum mechanics is the Heisenberg uncertainty principle. And one way to state it is this. It's that the more precisely a particle's position is determined, the less precisely its momentum can be determined, and vice versa. So what that means is if you measure its position to more and more decimal places, you will not be able to measure its momentum very much, or to fewer and fewer decimal places, and vice versa. And because of Heisenberg uncertainty, quantum mechanics is probabilistic, because you can't be certain where a particle, always be certain where a particle is or how fast it's moving. We have to deal with probabilities and statistical uncertainty. So what does that mean? Well, I'm a theoretical physicist, so what I want to do is take some equations, do some calculation, and get a number that I can compare to an experiment, some kind of prediction. And that's the way things worked before quantum mechanics. However, once quantum mechanics comes around, things are a little different. I don't just calculate one number. Instead, what I do, I calculate numbers for all possible outcomes of the experiment. So I have to consider all the possible outcomes of the experiment, and then attached to each outcome is some probability of obtaining that particular outcome. So for example, outcome number 1 might have a 20% probability, outcome number 2 might be 15%, and so on. And a key point that people often misunderstand is that even though quantum mechanics is probabilistic, it's still very predictive. It can make predictions. It's just the prediction's a little different. The prediction is not that if you do the experiment once, you'll get a certain number. The prediction is if you do the experiment 100 times, well, 20 times you'll get outcome number 1, 15 times you'll get outcome number 2, and so on. However, because it is probabilistic, it does change our view of reality, especially at these subatomic scales. And so to illustrate this, let's consider the simplest atom, a hydrogen atom. So here's an artist's very crude depiction. A hydrogen atom is the simplest possible atom. It's just the nucleus is just a single proton, and there's a single electron orbiting around it. And this is the picture that you might have, but in quantum mechanics, this is actually not correct. In quantum mechanics, instead, this is what a hydrogen atom looks like. So what you're looking at are the three axes, the three directions, x, y, and z. And then what I've shown here is this cloud you're looking at is a probability density. It's the probability, in this case, the probability of finding the electron somewhere. And the idea is that the denser that cloud is, the thicker the cloud, the higher the probability, the higher the likelihood of finding the electron at that particular position. And what you notice right away is that actually the electron can be at any position because of that Heisenberg uncertainty, but there's different probabilities of finding it in different places. And in fact, the most likely place to find it is at the origin there, right at the center. And by the way, you can make a similar figure or picture like this for the proton in the hydrogen atom. It's a much harder calculation. The main difference is it's a much denser cloud and it's much more concentrated around the origin. So in fact, this at microscopic scales, this is what the world looks like. But crucially, as I said, even though quantum mechanics is probabilistic, it's still predictive. And in fact, going back to the standard model of particle physics, which is quantum mechanical, it is probably, and I think it is actually, the most successful theory in all of physics, because it can describe very accurately to many decimal places an enormous number of different phenomena. So I've summarized some of those here. So for example, it can describe electricity and magnetism, basically any electromagnetic effect like static electricity, lightning, light bulbs, magnetism like your refrigerator magnet. And it can also essentially describe all of atomic physics because it can explain quantum mechanically the structure of nuclei and atoms. And so it can explain the structure of the periodic table, and from there, ultimately, basically all of chemistry. Not only that, it can also describe radioactivity and nuclear physics, both good and bad, including nuclear reactions in power plants, nuclear power plants, as well as in atomic bombs or nuclear weapons. And it can also describe the nuclear reactions happening in the sun, which are driving all the sun's heat and light, which is the reason that there's life on Earth. So the standard model of particle physics is extremely successful. It's great, it's wonderful, it describes things at microscopic scales, but there's a big problem because there's a big thing that it's missing. It does not describe gravity. So it can describe the nuclear reactions happening in the sun, but it cannot describe the gravity that's actually holding the sun together. That's obviously a big problem. A little bit of an oversight there. Luckily, it takes me to the other major achievement of 20th century physics, namely Einstein's theory of relativity, because that is a theory of gravity. So I'm going to try and explain that pretty quickly. So going back to the history first, Einstein's theory was developed, again, before the Second World War, actually between the wars, sort of right after the First World War, the 1910s and 1920s mostly. It was developed mostly by Einstein. He had the major conceptual breakthroughs, although immediately afterwards many dozens and hundreds of other people started working on it, but the breakthroughs were his. So I'm not going to go through all the details of Einstein's theory. I'm just going to try to give you an idea of it. Einstein's starting point, which was kind of radical, is the idea that space and time are malleable. So you should not think of a point in space and time as being rigid and fixed and it's not going anywhere and objects are moving through it, or moving through space. Rather, you should think of space and time themselves as being malleable substances like silly putty or clay or bread dough. So they can bend and stretch and warp and deform. And they can also do things like expand and contract. Space and time can expand and contract, just like bread dough rising in the oven. And in fact, that's what our universe is doing right now. You may have heard, because of the Big Bang, the universe is expanding a lot like bread dough. And Einstein's key point was that, the amount that space and time bend or curve or warp is related to the amount of mass or matter that's in the space. So if you have a very light object like this red ball, it'll warp space and time a little bit. If you have a heavier object like that orange ball, it'll warp space and time more. And if you have a much heavier object like that yellow ball, which could be, could represent the sun or some large object like that, it'll warp space and time a whole lot. And the idea is that the strength of gravity, what we perceive as a gravitational attraction or the gravitational force, is related then to the amounts of that bending and warping. So that, for example, in this picture, if that big red thing in the center, the big red ball is, say, a star, it's warping space and time a whole lot. And so then if some other small object comes along, like a planet or a comet or something, its trajectory will change. It'll move in a different way. And in this case, it could, for example, get trapped in an orbit around the star because of that warping. So in a very quick nutshell, that's Einstein's theory, that what we observe as the gravitational force or gravitational attraction is actually just coming from the fact that massive objects or matter bend space and time, and then that can influence the motion of other objects, and vice versa. So in this picture, the small object would also be bending space, but if it's much smaller, that's a very small effect. It'll affect the star a little bit, but not very much. Anyway, again, in a quick nutshell, that's Einstein's theory. Now, broadly speaking, Einstein's theory describes the very big, so things on very large scales, and in particular things with a lot of mass, or a lot of matter that warp space a whole lot. So for example, Einstein's theory can very accurately describe the orbits of satellites around the Earth. This is an artist's conception. But what kind of distances are those? Well, here's where the big numbers come in. So that's about a typical size of a satellite's orbit around the Earth is about 30,000 kilometers. Einstein's theory can also very accurately describe the orbits of planets around the sun. Again, this is an artist's depiction. How big is that? Well, it's on the order of 10 to the 9 kilometers, or a billion kilometers. And even bigger. So for example, Einstein's theory can describe very accurately the motion of stars in our galaxy, the Milky Way. This is an artist's conception. Obviously, nobody's taken a picture outside of the Milky Way since we're in it. But anyway, how big is a galaxy? Well, a typical size of a galaxy like ours would be about 10 to the 18 kilometers. So now we're getting really big. That's a billion kilometers. And I can keep going. Einstein's theory can also very accurately describe the gravitational interaction of galaxies with each other. So now these are distance scales on the order of 10 to the 19 to 10 to the 23 kilometers. Those are the typical distances between galaxies in our universe. And I'll go all the way to the biggest scales that I know about. This big number, 10 to the 23 kilometers, that's the size of the visible universe. That's as much as we can possibly see, right? So the universe is about 13.7 billion years old. The speed of light is the fastest that anything can go. So just take rate times time equals distance. Largest distance we can possibly see is about 10 to the 23 kilometers. And again, this is an artist's conception. So on these very large distances, Einstein's theory is very successful. It describes the motions of all these objects very accurately, again, to a lot of decimal places. But Einstein's theory is also incomplete because it's not quantum mechanical. And what I want to try and convince you of is that's a problem because the real world has both, right? Both gravity and quantum mechanics. So we know that all these objects like planets, stars, galaxies, a lot of the stuff we see in the universe is made of those fundamental particles, quarks and electrons, and they're quantum mechanical. And they're producing, ultimately, the gravity between objects is coming from them. And yet we don't have a theory that describes both of those things. So the two major achievements of 20th century physics, quantum mechanics and Einstein's relativity, give rise to the, well, okay, usually we can ignore one or the other. You can ask, like, well, how can we have these two different theories where each one is incomplete and yet they're both so successful? Well, it's because usually we can ignore one or the other. So for example, if you're looking at just an individual quark and an electron or something, well, yeah, they have some gravitational interaction, but it's really tiny compared to, say, their electromagnetic interaction. So you can ignore it. And similarly, when you talk about galaxies or something, I mean, yes, there's electromagnetic interactions happening between the quarks and electrons, for example, but there's so much mass that the gravity actually wins, and it's a more important force, and it actually dictates the motion of the galaxies. However, and this is a key point, sometimes we can't ignore them. There are cases where both things, gravity and quantum mechanics, are really important at the same time. And broadly speaking, this is cases where you have an enormous amount of matter or mass, but in a really small space, like subatomic scales. So when does that happen? Well, one example is black holes. That's where you take so much matter, so much mass, you cram it into such a small space that becomes so dense and the gravity becomes so strong that even light cannot escape. Nothing can escape, not even light, hence the name black hole. And you may have seen this picture that was in the media recently, I guess, or at least within the last year or two, of people taking this actual image of a black hole. And another example, of course, is the Big Bang. So as I mentioned, the universe is expanding, but that means if you run the movie backwards and go back in time, eventually, well, the universe would appear to contract and eventually reach a single point. So imagine that, everything in the universe contracted to a single point. Well, obviously there, quantum mechanics will be important. That's a really important case, the Big Bang especially, because it's the origin of everything in the universe. And so it's a case where you need gravity and quantum mechanics, and it's the origin of everything we know, so it's really important that you understand both at the same time. And it would be really helpful to have a theory that can describe both at the same time, which at the moment we don't have. But anyway, the two major achievements of 20th century physics, quantum mechanics and Einstein's relativity, give rise to the major problem of 21st century physics, namely how to combine the two. Now this theory that we don't have yet, we don't know what it is, but we have a name for it. We call it quantum gravity. This mythical theory of quantum gravity that we're trying to find. It's sometimes called the theory of everything, where everything doesn't mean literally everything. Sometimes people get confused. It doesn't mean like art history and philosophy and politics. I mean, everything means all physical phenomena that we can observe. It would be one theory that describes all the physics we know. So as I said, I should mention before I get to string theory, a lot of people have worked on this problem for the last 100 years, since the Standard Model and Einstein's theory were developed. And they've all failed, lots of brilliant people. So it's still an open question, how to merge quantum mechanics with gravity. And that is where string theory comes in. Because string theory is currently our best candidate for a theory of quantum gravity. So first, the history. When was string theory developed? Well, it was the generation after the Standard Model. So it was really in the 1970s and 80s and into the 90s. And I've pictured some of the people involved here. I don't think any of these people have won Nobel Prizes. You'll also notice a theme. There's lots of white guys. So far, that's pretty much all I've shown. We're working on that. The progress is slow. But this is my opportunity to mention another personal connection. So my second physics job was at the University of Cambridge, and my boss was this guy, Michael Green, who was one of the founding fathers of string theory. So again, it was very intimidating, showing up at Cambridge, first of all, and then secondly, working for the great Michael Green, this sort of legendary figure. But it turned out he was really friendly and nice. He was a great boss, and I had a lot of fun there. So what is string theory? Just what's the basic concept? So again, I'll give it to you briefly. So string theory begins with a hypothetical, a question, namely, what if the electrons and quarks are not fundamental? What if they're made of something smaller? So now we're leaving the realm of experiment, as I mentioned, because as I mentioned, experimentally, the limits where we are now, as far as we know, the electrons and quarks are fundamental. We have no evidence they're made of anything smaller, so string theory begins with this hypothetical question, well, what if they are? And in particular, the main proposition of string theory is that these electrons and quarks are made of smaller objects called strings, hence the name. So if you want an artist's conception, here's one. You can imagine, say, if you looked closely enough at a quark, it would look like a little piece of string. Of course, every time I mention that, people always ask me, well, what's the string made of? Because when you say string, people think of yarn or twine or something like that. And of course, that's not correct. The point is, in string theory, the strings are the fundamental objects. Okay, that's the fundamental assumption of string theory. So they're not made of anything smaller. So if you ask, what are the strings of string theory made of? Well, I'll give you the answer that my PhD supervisor gave to me. He said they're not made of anything smaller, they're just pure energy. And so if you want an artist's depiction of that, here's a picture. You can imagine a little string, or I don't know what to call it, a strand of, or something of energy that can move around. However, okay, so why do we call them strings? Well, because the way they move is very similar to a string. So in particular, the idea of string theory is that the electrons and the quarks are made of the same type of string. We call it a string because it can vibrate, just like a violin string or a guitar string or a piano string. So for example, a violin string can violate at different frequencies, which I've shown here, which give rise to the different notes that we hear. And the idea with string theory is that although the electrons and quarks are made of the same type of string, well, what's the difference between them? Well, it's the frequency at which the string vibrates. So in particular, the quark is made of a string that's vibrating at a higher frequency than an electron. But it's the same type of string. Now, I'm going to skip a few steps because there's a lot of math involved, but what's remarkable is that just starting from that simple assumption, you can write down some equations, you can go do a bunch of calculations, and what you'll discover really remarkably is that string theory is a theory of quantum gravity. It contains within it both quantum mechanics and Einstein's relativity. So for example, it can describe quantum mechanical phenomena like the ones I mentioned before. It is probabilistic in the way that quantum mechanics is, but it can also describe gravity. So for example, it can describe the gravitational interaction between quarks and electrons. And I'll just emphasize that's really remarkable because, like I said, for the last 100 years, people have been working on quantum gravity and just failing over and over again. It's been very frustrating. People much smarter than I am, lots of brilliant people, getting all their best ideas, and they failed. But now, string theory comes along, and it works. At least it can combine quantum mechanics with relativity, but, of course, question is whether it's right. And, of course, in physics, right means you can test it experimentally, and it agrees with the experiments. So it's a perfectly fine solution in principle, but does it actually describe the real world? And so the key question is, can we test string theory experimentally? And, well, you can guess the answer. Of course, no. And there's actually a lot of reasons this is the case. But just to connect to the earlier part of the talk, you can ask a fundamental question. How long do the strings, or how big do the strings have to be in order for string theory to be a theory of quantum gravity? And again, you can go do some calculation. I'll just give you the punchline. In order for string theory to be a theory of quantum gravity, the fundamental strings have to be about 10 to the minus 33 centimeters long, which is 20 orders of magnitude smaller than the quarks, which is our current experimental limit. So 20 orders of magnitude smaller than our current experimental limit. That's why string theory has never been tested experimentally, and there are people who believe it might never be, that we may never be able to devise an experiment that could reach such a short distance. But physicists are very clever, so you should never give up hope. We've always found ways to make breakthroughs when people were hopeless. So in a nutshell, that's string theory. Okay, it's a putative or proposed theory of quantum gravity, which is already a remarkable achievement. That's something, that's progress. But then the next step, what's holography? So again, starting with the history, holography was developed basically in the 90s up until the present, so after string theory. And it was developed primarily by these three people, Susskind, 't Hooft, and Maldacena. 't Hooft actually does have a Nobel Prize, but not for holography or string theory. He won a Nobel Prize for his work on the Standard Model. But let's start with this guy in the middle, Maldacena. This is Juan Maldacena. He's originally from Argentina, but in 1997 he was at Harvard. And if we go back to that time, he was thinking about string theory, but with a twist. He had a new ingredient. He was thinking of string theory on a space with a boundary. So I've tried to draw a picture here. So you're supposed to imagine this is some space. I have string theory living there, so I have some strings moving around. But there's a boundary. So there's this wall, which is this blue rectangle. It's supposed to be in the background. It's a wall where the space ends. So the strings can move around in the space, but then if they try to go too far, they'll hit the wall and bounce off and come back. And they can't leave. So Maldacena was studying this, and he made a remarkable discovery. He discovered that there are quantum mechanical particles living at this boundary. They don't have any gravity, so it's kind of like the standard model of particle physics. It's a little more complicated, but they're basically quarks and electrons, and they're quantum mechanical, and they interact with each other, but they don't have any gravity. And when I say he found them living there at the boundary, what do I mean? Well, what he actually found is that these two things are equivalent. Now, this is potentially confusing, so let me try and explain. The idea is you have two sets of equations. One is the equations of the string theory, describing the motions of the strings inside the space. But he found that those equations were equivalent to a different set of equations. You could basically rewrite them in a different way. And this other set of equations describes something very different. There's these quantum mechanical particles, and they appear to be stuck at the boundary. So they can't move into the space. They're stuck at the boundary. They're quantum mechanical. They're not strings. They're just particles. And furthermore, they don't have gravity. So in other words, he found an equivalent description of the string theory. Or to put it a different way, he found two sets of equations that superficially look very different and seem to describe very different things, these particles versus the strings. But in fact, he discovered that they're secretly equivalent if you know how to translate between them. So it's a lot like having two different languages, like French and German. They might look very different superficially, but there is a dictionary between them. So to give you some intuition for how this works, I know this is all very strange. It was strange to me the first time I heard it. But to give you some intuition for how this works, okay, let's suppose I have a string moving around in my space. and let's say it's moving in some direction, well, what you'll see with the quantum mechanical particles is you'll see a bunch of them, not just one. You'll see a bunch of them bunched together and moving in the same direction as the string with the same momentum. And yes, they're both still subject to Heisenberg uncertainty. But of course, the strings can move in one extra dimension. They can move in a direction that the particles can't, because they can move away from the boundary or towards it. So what happens if that happens? Well, if the string starts to move away from the boundary, what you'll see is this bunch of particles will start to spread out. And then conversely, if the string moves towards the boundary, they'll actually bunch closer and closer together. So in other words, the size of the object there, of this group of particles, actually encodes the depth into the space where the string is. So that's how the particles know how deep the string is into the space, even though the particles never actually leave the boundary. And so intuitively, you can think of it as if the string is actually casting a shadow on the boundary, and the shadow is made of these particles. So why is it called holography? Well, I don't know, maybe it's obvious, but I'll explain. Well, first of all, okay, in the real world, what's a hologram? Well, you've probably all seen an actual hologram because every credit card has a hologram on it, a hologram of a bird flying, and the reason they do that is because a hologram is very difficult to counterfeit. But anyway, in the real world, a hologram is a two-dimensional or flat image, but it contains enough information to reconstruct a three-dimensional object, like a bird. And so hopefully it's clear that something similar is happening here, that these quantum mechanical particles, that theory, those equations, contain all the information of the string theory in one higher dimension. So in other words, those particles, that system of particles, are actually the hologram of the string theory. Hence the name holography. And in fact, these guys, Susskind and E. Tufte, actually elevated this to a principle, saying, well, this is not special to string theory. This actually should be a fundamental property of any theory of quantum gravity, so that even if string theory turns out not to describe the real world, well, we still think quantum gravity exists, and we still think this holographic principle will apply. Namely, the holographic principle, just to state it, it's the idea that any theory of quantum gravity is holographic in this way. So if I have just some quantum gravity living in some space, well, at the boundary of that space, there will be some quantum mechanical particles that somehow, in some way, contain all the information of what's happening inside. It's not a very helpful principle because it doesn't tell you anything about the particles, like how to find them or what are the equations that describe them or anything. It just tells you that they will exist. But it's still significant because it's actually telling you, if you think about it, it's suggesting that quantum gravity is much simpler than we think, right? It's not some complicated combination of the Standard Model and Einstein's theory or something, or doesn't even necessarily have to be a string theory. Quantum gravity could ultimately be described just by something like the Standard Model, just some quantum mechanical particles. So it's potentially a big simplification. Okay, so I know that was a lot, and there's a lot of questions, like how does all of this work? How does the dictionary between the two work in detail? I gave you a little bit of intuition, but not very much. There's also sort of big questions like, well, in our universe, we believe quantum gravity exists, so does our universe have a hologram? So out at the edge of the universe, are there actually some quantum mechanical particles that somehow know everything that's happening in the universe? Conversely, you can turn it around and say, well, we know the Standard Model, that's some quantum mechanical theory. Is it the hologram of some other theory of quantum gravity? And then, of course, a big question is, can we test any of this experimentally? And how would you even do that? It's difficult to imagine tests of the holographic principle. And I'm actually not going to go through any of these questions. They're all enormously important questions, but they're all topics of cutting-edge research that's happening right now. So I can't actually answer them. I could give you the state of the art, but I can't give you the answer. What I am going to do is I'm going to tell you something else that holography is good for, which brings me to my third part of my talk, namely strongly interacting systems. So what are those, and what do they have to do with string theory and holography? Okay, so to describe strongly interacting particles, I'm going to start with something very simple, something we give our undergraduates as a homework problem, namely free particles in a box. All right, so just imagine you have a box, and there's particles moving around it, inside of it, and they'll have some momenta, and when they hit the walls of the box, they bounce off and keep going. Fine. So the simplest possible thing in this box is if you have non-interacting particles, or a non-interacting system. So what does that mean? Well, that means the particles don't interact at all, which means that in what they would do is they would just pass through each other. So if two of them approach each other, well, if they don't interact at all, they'll just keep going, pass through each other. It's kind of ghostly if you think about it. But why do we consider this? Well, because it's really easy to solve for their motion. If they never interact with each other, then once you know its momentum and position at one time, you can predict it at any later time. And so therefore, this class of systems, non-interacting systems, is completely under control. This is considered a solved problem in physics. And we can tell you, in principle, we can tell you anything about such a system. If you have non-interacting particles in a box, we can tell you where they will be at any time. We can tell you the temperature and pressure of the box. It's a solved problem. But of course, it doesn't describe the real world. So we need to add a layer of complexity. Let's go to the next step, which is a weakly interacting system. So in this case, what we do is we allow the particles to interact, but only weakly, so only a little bit. So what that means is if two of them approach each other, each one will give each other a slight kick, or a weak kick, or a weak push. So you can imagine, like, say, two electrons will push against each other, something like that, but a weak one, not very big, and in particular, each one will experience only a slight deflection to its motion. So this case, it's not a completely solved problem, but it's mostly solved. It's mostly under control. We have a lot of techniques that have been developed over the last couple of centuries, actually. And so we can calculate almost anything you want to some degree of precision. Not everything. There's still open questions, lots of interesting open questions, but for the most part, it's considered a solved problem. The major open questions are considered solved. But of course, that brings me to the topic of my talk, namely strongly interacting systems. So in this case, again, if you imagine the particles in the box, if two of them approach each other, if they're strongly interacting, each one will give the other a very powerful kick. So bang, they'll bang off each other, or ram into each other really hard. In that case, each one can experience an enormous deflection, some radical change in trajectory. In this case, generally speaking, is not under control at all. It's considered a major open problem in physics. In a lot of cases, we have no idea how to approach the problem. There are some special cases where people have made a lot of progress, but in general, it's an open problem, which of course is why people work on it. Including people like me. And one of the main things I want to get across is that it's not just hypothetical. There are real systems in the real world that involve strongly interacting particles. And they're really important because some of them have potential applications that could revolutionize the world in a lot of ways. So I'll give you some examples. I won't go into any details. I'll just throw out the names. One example is high-temperature superconductors, and there's a photograph of one on the upper left. That little piece of, it looks like gold. It's not actually. I won't go into the details, but these involve electrons that interact with each other very strongly. What's remarkable about them is they can conduct a current with almost no loss of energy. And so if you could make power lines out of high-temperature superconductors, we could save, 20% of all the energy lost every year. Which would, of course, be great for the environment and the economy and lots of other things. Another example are topological insulators. That's the middle picture on the left. And again, without going into details, I'll just say these are materials that could potentially be the basis for quantum computing, a new generation of computers that are enormously faster and more efficient than our existing computers. And a third example I'll give is graphene. If you don't know what that is, it's carbon. It's just carbon atoms. And I have an artist's depiction down there on the left. Graphene is carbon atoms arranged in a honeycomb lattice, and it's a single sheet. A single sheet of carbon atoms in a honeycomb structure. And it's a really remarkable material. It's super strong, and it can bend and twist. It's very strong. It can conduct a current really well. And so if you could scale it up to the size that you could build, some technology out of it, it could have remarkable applications. And on the lower right there is a picture of one proposed idea. This has not actually been built. This is a proposal. It's the idea that using graphene, you could make something like an iPad, only it would be as thin as a sheet of paper and transparent. I'm not sure why you would want it to be transparent, but it could be because graphene has its optical properties would allow for that. Anyway, these are all materials that involve strongly interacting electrons, and they have remarkable properties that would have these remarkable and potentially revolutionary applications. So that's why this is a big problem in physics, to solve strongly interacting systems. So what does this have to do with string theory and holography? Well, let's go back to holography. So here's my picture with my string theory in this space, and then living at the boundary, my quantum mechanical particles, which are the hologram of the strings. So what I didn't tell you was that when the strings are weakly interacting, the particles are actually strongly interacting. And that might be a little confusing because the particles, a single string is supposed to be described by a little bunch of these particles, and how can the string be weakly interacting in the way that I described when the particles are strongly interacting? It's like, well, it's because the particles inside that little bunch are all strongly interacting with each other, but the whole bunch by itself as a composite object, has this object built of the little guys. That whole thing, if it interacts with another lump of particles, they will actually appear to be weakly interacting with each other, even though the individual particles are strongly interacting. Anyway, I won't go into any more detail about that. The point is that the particles are strongly interacting. And this is what I use in my research. Okay, so here's how my research works. I can now summarize for you how my research actually works. What I do is I go to these systems in the real world that involve strongly interacting particles, and I ask questions that we don't know how to solve using any other technique. I then go to my holography, and I formulate that question about my particles there. Now, I formulate my question about the particles there. I then use holography as a dictionary to translate to the string theory side. And the strings are weakly interacting. So I can write down some equations for my strings, and they're weakly interacting, so I know how to solve them. I can use existing techniques to solve those equations, get an answer, and then again, using the dictionary, translate back to the particles. And I can get an answer about a strongly interacting system that I could not get any other way. Now, of course, there's a price to pay, is that the string theory and these quantum mechanical particles don't describe any particular real system. It doesn't exactly describe graphene or high temperature superconductors or topological insulators. So what's the point? Well, it's the only way we have to solve strongly interacting systems, so it's worth studying for that alone, because we're hoping to learn general lessons, right? You're looking for general principles or some kind of universal principles or laws that could apply to the real systems. So even though you're not studying the real systems, you're studying very similar classes of systems that might reveal patterns and principles that are applicable to the real systems. And so in that way, you hope to make progress with the real systems and potentially make something like a prediction. It may not be a specific number, but maybe some behavior or some general property. Again, some general or universal property or principle. Anyway, I've talked enough. But hopefully now you have some idea what I mean when I say that in my research I use a tool from string theory called holography to study strongly interacting systems. I just hope you have some idea of what each of those things is, why it's important, why people care, and why people do research on these things. And in particular, my punchline, so if you only remember one thing, if you ask what is string theory good for, well, of course, there's one answer, which is that it's currently our best candidate for a theory of quantum gravity. But there is another answer which doesn't get out to the public as much, which is that it's also a useful tool for studying strongly interacting systems in the way that I described, because of holography. Finally, I'll just mention that a lot of people work on this. I'm not the only one. And even just here in Southampton, at the University of Southampton, we have, I think, at least a dozen people. These are all lecturers in the physics and math departments who are all working on these topics and topics closely related to them. We don't all work on exactly the same things. As I mentioned, there's lots of open questions about all of this. And so all of these people work on different aspects. So I'm just part of really this big team working on all these different things. And finally, if you want to know more about this, hopefully you do have lots of questions, but there are some good books. There's one I recommend by Brian Greene called The Elegant Universe. There's one by Joseph Conlon called Why String Theory, which tries to explain, both of these try to explain in more detail most of what I talked about some of the history of where string theory came from, about quantum mechanics, Einstein's theory, and so on, and then string theory, what it is, how it's defined, how you do calculations and things like that. But it's for a general audience, so there's no equations. And of course, you're welcome just to email me, and that's my email address at the bottom, and ask any questions you might have anytime. I'm available all the time. I'll try to get back to you as soon as I can. And with that, I'm done. So thank you for listening. I hope you learned something. I hope you enjoyed it. And I hope you have lots of questions that you will pursue in the future. If you do, let me know. And thanks for listening.